Okay, guys, let's try to take a look at the answer together. Try to solve it together. Again, you have to solve it on your own later on, okay? But let's look first at the gas. No, the oil. The oil is first. So the oil here. There are several plots in the report. Probably this is the one that you want to look at. What was the question? Well, first question about the gas. I noticed that there was a little bit of confusion about the question, but I don't really care about the exact answer. I just want you to be aware that with this homework, that the gas from shale is actually a lot. As you can see, this plot has been growing with time. And now, if you consider all of the gas coming from shale, it's what, 80%? It's a lot. Only from the Permian, it looks at about 20%, and almost 30% appears to come from the Appalachian basin. You know that now Pennsylvania exports gas. Before they couldn't cover the internal supply, now they export LNG to several other parts of the world. And all of these comes from fracturing. Let's look now to the oil. Where is the oil? I strongly recommend that you read through this. It's not a lot of information, but it will be very useful to have an idea about the current outlook of oil and gas production. So, LTO. LTO, that stands for light tight oil. Sometimes the definition of a shale, it's a little bit arbitrary. Anything which is tight nowadays is called, or some people call it shale. But shale, from the point of view of geology, actually has a very specific meaning. It requires to have a lot of composition of clay minerals, clay particles, but there are some tight oil which is not, actually doesn't fall in that category. So that's why they call it here light tight oil. That comes from tight formations that require hydraulic fracturing in order to be produced. And as you can see, with respect to 2010, it grew a lot. It appears to be here something about 7, here is equal to 1,000 barrels. I guess this is the number per day. Although the number is a little below. And it has grown a lot. When did you guys got to UT?
2016.
16, right? Somewhere over here. I got here in 2013. At that time, there were people that were saying that the shale oil production will peak and will fall down around that time. And it hasn't peaked, it didn't fall. It might in the future, but the unique characteristic about shales is that they are almost not everywhere, but here in the US there are a lot of basins where you can produce it. And as long as you have the capital to do it, probably you'll get some oil out of it. Okay, all right guys, so that's about the introduction. Please complete the homework, put that together into a Word file, or even if you just do it on a piece of paper, that's fine. Convert your Word file to a PDF, or take an image and scan your piece of paper and upload it to the Canvas website before Friday next week, 11:59 p.m. Okay? So this first homework is not a lot of work. So probably you finish it today, you upload it today, and that's done. Next one, it will take a little more of work. So let's get started talking about chapter number 2. In chapter number 2, you have it already here. we're going to talk about pore pressure. That's something that you know, but there's going to be one more thing new that you're going to see, and about total vertical stress. Probably something that you do not know. We will start our discussion with pore pressure. Today is, what is today? 27? 25th.
2, 3,
2019. And we're going to talk about pore pressure. Are you guys familiar with the Balcones fault? What is the Balcones fault? I hear yes. No? Okay.
It just says how many times it increased.
Yeah. So okay, so we're here, you know, on this side of the Balcones fault. All the hill country also is on the other side of the Balcones fault. Actually, if you go to Barton Springs, Balcones fault also goes to that. So this is Barton Springs. And I like to go over here and just hang out over there. Okay? Next to Barton Springs. So this is the pool, and this is the fault. My question is, if this is a fault and all of this is water, how does pressure increase with depth? Let's start by looking first at the pool. How does pressure increase with depth inside the pool? Linear here. Why? Why linear?
Hydrostatic.
It's hydrostatic. It's a constant gradient. The weight of water, we can assume that as constant. And as long as you're inside the pool, this is going to follow a linear trend. What is the equation for that?
Rho GH.
Rho of what?
Water.
Rho water
GH.
times G times H, where H is depth, but let's call it Z for coordinate C for depth, okay? What about as I go deeper into the fault? And let's say this fault is thick enough that there is a well-connected body of water that goes inside. How the pressure is going to increase? Will it increase also linearly, or will it change? Now we're getting into a fractured rock system.
It should increase linearly.
Linearly. If the water is consumed compressible.
As long as the water is connected and there is a path that connects this to whatever point inside the cavity you have, it's going to increase linearly. It's going to follow the same train as the one that you have in the bulk water. We're going to see that this is going to change later on, okay? But as long as there is a connected pore or fractured space, this is going to increase linearly. Even if you have, in this rock, if you have some fractures in it, inside the fractures, as long as the fractures are well connected to the top, to this free surface, anywhere in here, the pore pressure is going to increase linearly. If you have, for example, a rock which is a sandstone, as long as the pores in the sandstone are well connected and hydraulically communicated to the top, the pressure will increase linearly according to this relationship. So this equation, we can break it in two, and we'll see that that's going to be very useful later. On this side, we have depth. And on this side, we have something else which usually goes by a gradient. And in this case, if we have hydrostatic pore pressure, it's going to be a hydrostatic gradient. Do you guys remember what is the value of this gradient? Let's say let's take an average, okay? Let's say 0.44. What?
PSI per foot.
PSI per foot, right? Okay. Those are the field units. But we're also going to be using the SI system, the international units. And in order to do that, we're going to also calculate what this gradient is, but with metric units. So let's try to put these equations in terms of the metric units. What is the density of water, more or less, in metric units?
1 cc. 1 kilogram per meter.
So, gram, be careful, okay? Because gram and centimeter cube is not the SI system. It,
1 kilogram.
yes, it should be kilogram, meter, second. That's the international system. If you use grams or centimeter cube, that's a CGS system. It's similar to the other one, but it's not exactly that one. So let's use the SI system. So what is the density of water?
1,000 kilograms.
Let's say 1,000 kilograms per meter cube. And what is the acceleration of gravity? 9.8. Well, let me simplify this a little bit. I'm just going to write 10, okay? Because I want to make this example a little bit simpler. 10 what?
Meters per second
Per
squared.
second squared. Okay. So we're halfway to solving this. What is a kilogram times meter per divided second squared?
Oh, no, sorry.
It's in Newton, right? So mass times acceleration is force, is Newton. And I'm going to go further here and make this 1,000 times 10, 10 to the 4. This is Newton. And I'm going to break this meter cube into two parts. Meter squared and meter. It's the same, right? And what is that? That's a Pascal, right? So this is 10 to the 4 Pascal. And in order to make my numbers a little bit simpler to deal with, I'm going, instead of meter, I'm going to use kilometer. So how many kilometers is a meter? How much?
0.001.
Or 10 to the minus 3, right? 1,000 of a meter, of a kilometer. That's 1 meter is 1,000 of a kilometer. All right, and what is 10 to the 4 divided 10 to the minus 3? 10 to the 7, very well. This summer I was helping my nephew with all these power laws. I spent like probably 3 days trying to teach him this. He still is having trouble with it. I'm glad that you guys know how to deal with this. So this is going to be 10 to the 7, right? Instead of 10 to the 7, I'm going to write 10 to the 10 to the 6. 10 times 10 to the 6, which is the same, right? So this is going to be 10 and 10 to the 6 Pascal divided 1 over kilometer. Finally, it's going to give me the value I'm looking for, which is 10 megapascals, where this is an M, capital M, per kilometer. This is the gradient of work pressure, hydrostatic pore pressure gradient in terms of the metric units. It's exactly the same with the field units, but here there is always a lot of confusion. So let me explain what's going on here. Always, you know, I get the question, well, where does G go? Why don't we multiply times G? Because here we did, right? There we have G. It was 10. Why we don't multiply times G over here? Well, let's work through that. What is the density of water in field units?
62 pounds per foot.
Let's say 0.4, okay? Pounds per. Okay. So if we're talking in terms of mass, that's fine, okay? So 62.4 pounds per feet cube. We can also write density of water times G already with the G in it if we talk in terms of force. So this is going to be 62.4 now pounds force divided feet cube. And that one already has a G in it, okay? You don't have to multiply by G. This is a force. It's a pound force. And this is the one that we're going to use. So how do we convert now this to PSI? And it's not only that, but what my result, I like that one to look as PSI per foot, okay? So, in order to do that, what we're gonna have to do is, we're gonna put aside here the pound force, we're gonna leave here 1 foot and 1 foot squared. We're going to bring it over here. So 1 foot is 12 inches, and this is gonna be 1 foot squared. So calculate how much is 62.4 divided 144. Can you guys do that?